Okay, so here we go. It looks like most of you have commented about the street sign, the rock, and the grass. And it looks like everyone has a good understanding of specific heat. And it also looks like I might have fooled you with the previous video. The idea of specific heat is that specific heat is how well a material can absorb heat or release heat, or how well it can easily change its temperature. That's basically what specific heat is. So previously we asked, you went outside, you looked outside and you saw a street sign, a rock, and the grass. And the question was, rank the objects in order of their temperature. And what most of you had said was, all of these objects are the same temperature because they're all in the same room and they reach equilibrium. Basically the same thing that I said about the steak knife. And the idea here is that I think that your answer was biased and based upon not what you have in your noggin. Because if you looked outside, the key point there was that if the sun were out, this would be a different story. But I said before the sun came up. So that means no sun, all right? So the sun's not there. So what you have to ask yourself is, when you look outside, where do you see frost and dew? Well, the obvious answer is going to be grass, right? Have you ever seen frost or dew form on a street sign and not on grass? No. First place you see it is on grass or dew. Okay, so what does that mean? Well, frost and dew basically are going to be the temperature is going to reach a certain point called the dew point. And if the temperature reaches a certain point, it's cold enough, then what's going to happen is the water vapor in the air will come out of saturation and it will condense onto whatever the material is that has the lowest temperature. So when you look outside, you know that the dew forms on the grass, so you know that the grass has to have the lowest temperature. All right, that's all good and fun, but we need to understand why. All right, and to understand why, I'm going to give you a story. So one day, now I know there's not a visual that comes with this. There's a story that goes with this. One day I was traveling on the road, on Canisteo Road, if you're familiar with it. There is one straight road, and on one side of the road is a reservoir or a lake, whatever, it's water. Okay, on the other side of the road, it's just the Newark watershed. So you got a whole bunch of wildlife over here, wild lands, or whatever you want to call it. So I'm driving up Canisteo Road, and as I'm driving, it is raining. And when I say raining, I mean it's a downpour. And the downpour is coming down so heavy, and it's also the beginning of spring. Well, it's the end of winter. But it's the first downpour since we've had snow. And as I'm heading up Canisteo Road, the downpour is coming down. All I see is just the drops in the road, and I think that there's a whole bunch of drops. Turns out it's not drops. And the headlights, as they're shining, what I'm looking at is I see a whole bunch of frogs crossing the road. And as frogs cross the road, they are crossing with the rain coming down. So all I see is the rain droplets coming down and frogs. Now, when I say frogs, plural, I'm not talking about 10 frogs. I'm not talking 100 frogs. I'm not even talking 1,000 frogs. I'm talking tens of thousands of frogs. Tens of thousands of frogs crossing this road. Where are they going? Obviously, they're going to the reservoir. So, why? Why are all these frogs crossing the road at the same time? Well, right before winter time, what happens is, here's the ground, and all these frogs, that's my best frog. All these frogs are going to burrow down under the ground. And when they get deep enough, they're going to stay down there. And when they stay down there for a reason. Why? Well, what happens is underneath the ground, there is a source of heat. And that heat is going to be warmer down here than it is on the top. Up here, it's going to be very cold and frozen. Now, the majority of frog is made of water. So if the frogs are out there on the top of the, well, not tundra, but just the flat ground, if they're up there and it's too cold, they're going to freeze. And what does frozen frogs do? Well, they don't do anything because they're dead. So what the frogs do is they burrow down underneath the ground where it's a little bit warmer. Why am I telling you this? Because the ground gives you heat. The ground gives you heat. So let's take a look at that same problem again. Here's the ground. Here's the street sign. Here's the rock and the grass. Okay, so I think what we had said was specific heat is how well an object could change its temperature, meaning how much energy is needed to change its temperature. If it's a little, then it has a low specific heat. If it's a lot, it's a high specific heat. So what do we know of that has a high specific heat? Well, what do we know of that takes a long time for it to change temperature? Well, it could be water. How long does it take to boil an egg? Well, it takes a long time because water has a very high specific heat. Specific heat of water is 4,180 joules for every kilogram to change it by 1 degree Celsius. That's a lot. Even though joules are a very small amount, 4,000 of them are needed to change the temperature of 1 kilogram by 1 degree Celsius. All right, that being said, we know that if you put your hand on the street sign, the metal pole here, then what's going to happen is that metal pole is going to take the heat from your hand away a lot faster. So that tells me that the metal pole has a very low specific heat. The grass, however, well, what is the grass primarily made of? It's primarily made of water, so it has a very high specific heat. And then the rock is somewhere in between. So underground, or the ground level here, I'm going to have a heat source. And that heat source is going to be transferred from one object to the other, meaning the ground up. Okay? So if I have heat, now remember, the sun is not out. So these temperatures are just the same as the temperature of the night around it. So if the ground were not here, yes, everything would be the same temperature. But the ground is supplying some heat. Ask worms. Okay? The heat here, if I add heat to this street sign, what's going to happen? Well, it has a very low specific heat. So therefore, if it's a low specific heat, what I'm using here is this. Q is equal to MC delta T. Okay? So if I have the same amount of heat, I'm looking to find out how does C interact with the change in T? How does the specific heat relate to the change in temperature? Well, if the specific heat is very low, then the change in temperature is going to be very high, right? So that means that if this is very low, then it doesn't take a lot of energy to change the temperature. So therefore, this is going to have a very high temperature, which goes against everything that you would think, because if you go outside and you touch the street light, the street sign, it's a metal pole. Oh my God, this thing is so cold, right? Okay. High specific heat means that it requires a lot of energy to change its temperature. So if I had, say, 10 joules here, 10 joules there, 10 joules there, what's going to have the higher specific or higher amount of change in temperature? Well, that's going to be the grass. Change temperature is going to be the street sign. So the grass is going to have a very low temperature. So it has the same amount of heat transferred, but what's that heat going to do to a low specific heat? Raise the temperature a lot. What's that heat going to do to a high specific heat? Not much. And then the rock is going to be somewhere in between. So what has the lowest temperature? The lowest temperature is going to be the grass. Why do those frogs go underneath the ground? Because of this bad boy right here. This heat is basically what's keeping them alive for the winter. Huh, didn't know that, did you? Well, if you did already, I think, congratulations, Mike. I think you were the only one that put the correct order. The lowest temperature being the grass, the highest temperature being the street sign. And again, it's the opposite of what you would expect. Why is it the opposite? Because although this is a higher temperature, it has a lower specific heat. So if I go and grab the street sign, then what's going to happen is it is going to take away the heat from my hand faster than the grass is going to take away the heat from my hand because of that high specific heat. Okie doke. So far, so good. Let that marinate for a second. So, all in all, the grass is going to have the lowest temperature, and the highest temperature would be the street sign. That leaves the rock in between. Okay? The proof is in the pudding, right? If I look outside, where do you see the frost? You see the frost on the grass. You see the frost on the lowest temperature. And again, have you ever seen frost on a street sign and not on the grass? Well, sure, if it's in a greenhouse, well, that's a different scenario, okay? All right, so now moving on, we had this heat being radiated from the ground. So let's talk about our 3 ways we can transfer heat. We can go from one object to the other. There are 3 methods of heat transfer. Anybody want to take a stab what they are? I'll give you a few seconds. Okay, all right. Heat transfer 1 is called conduction. Conduction is going to involve direct contact. Direct contact. Okay, so what would that be? What would be an example of conduction? Well, boom. You've all done this before, right? Direct contact would be I have this hand and this hand. When they're in contact with each other, the heat is going to transfer from one object to the other if they have a difference in temperature. So what would that mean? Okay, if I have this knife, I'll go from this side. If I have this knife and the knife is a different temperature than my hand, then the heat transfer is going to go from my finger to the knife. Does it travel this way? No, it does not. It doesn't travel until I come in contact. So direct contact would be conduction. And an example of conduction would be if I turn the oven on, or I turn the stove on, and I go and touch the stove burner. Ouch. That's direct contact, burn. 2, I have what's called convection. And this is going to be a big one that I'm going to probably sidetrack on for a good number of time on here. Convection is heat or energy transfer by way of movement of a fluid. Now, physics is very simple. Fluid, what is a fluid? Fluid's definition is, Fluid, the definition of a fluid is anything that has the ability to flow. Water has the ability to flow. Ask a river. Wind has the ability to flow. Ask a screen. Gas has the ability to flow. What's the purpose of a gas line? To flow through it, okay? Anything that has the ability to flow is a fluid. So let me give you an example of convection. Here is a rundown of room 108, okay? And room 108, it's really small. I should make it a little bigger. Got more paper here. Room 108, just in case you guys don't know, room 108 is our room in the high school. So room 108 has a heater, okay? And the heater in the back is going to be heating that air above it and pushing it out. That air is going to be moving away as hot air. And when it gets to the top, it starts circulating around this way. And it gets further away from the heating source, so it cools and it sinks down. And when it sinks down, it eventually comes back to the heater, heats up again, and we have what's called a convection current. So if I'm in the front of the room, how am I comfortable in the front of the room? I'm not actually sitting on the heater, right? Nobody is in direct contact with the heater, so the room 108 is not being heated by way of conduction. It's being heated by way of convection. Convection. What's another example of convection? Well, convection would be, convection current would be like your oven. So in your oven, you have a convection oven. And let's see if I could draw this pretty well here. This is where you put your bacon, right? And if your bacon is sitting on a little skillet over here, what's going to happen here is you have an under there is where your heat's coming from. And your heat is then going to be coming up to the top here. And as it comes back down, we're going to be circulating around and around. And it circulates around and around, giving you a convection current, which is then going to heat whatever's in your oven. Where do you place the food? Well, it depends on what you're cooking. All right, you want to put it up top, you want to put it on the bottom. It also depends on where your burner is going to be as well. But convection oven is by movement of the fluid. The fluid would be the hot air inside the oven. Okay, third type. If I'm not heating something up by way of direct contact or movement of a fluid, how else can I heat something up? You probably use this all the time, especially now if you're all isolated. I know I am. TV dinners. The Hungry Man TV dinner has never been such a best friend to me. Okay, so how do I heat up a TV dinner? I'm not going to heat it frozen, right? I'm not going to heat up a TV dinner by taking it and putting it on a flame. That's ridiculous. I'm not going to take a TV dinner and heat it up by blowing hot air on it from a blow dryer. No, that'd be crazy. But what I'm going to do is I'm going to use my microwave. And that form of heat transfer is radiation. Radiation is heating something up by way of electromagnetic waves. What are electromagnetic waves? Well, hopefully you had this in chemistry. Electromagnetic waves are anything from gamma rays all the way down to radio waves. You also got your visible light in there, your ultraviolet, you got your infrared. Okay, all of these things are going to fall within electromagnetic waves. Good example of radiation would be if I go out on a hot day, I'm going to heat myself up from the sun. Now, am I in direct contact with the sun? No. Is there fluid between the sun and the earth? No. So the heat is transferring from the sun to the earth by way of radiation. All right, so those are your three forms of heat transfer. I want to go back to this bad boy right here and fill you in on something. Okay. We talk about probably what you had in 7th or 8th grade. And that's going to be earth science. Or whatever they called it over there in La La Land. So here is the core. And then above the core is the mantle. And then above the mantle is the crust. Solid, not solid, solid. The core is made of nickel and iron, and it's going to be a solid core. The key thing here is that on the outside of the crust, it's very cool, which is going to solidify anything that makes it to the surface. However, the core is so hot that it's going to melt what's on top of it, and that's the mantle. The core is basically pushing out a whole bunch of heat. That heat is now going to be pushed to the top. And when it gets to the top, slightly curved at the top here, spherical, it's now going to push the plate away. Well, I didn't give away it's a plate yet. Dang it. Okay. And then when it gets away from the heating source, it's going to slowly cool and come back down. And then it's going to heat up again giving you a convection current. Okay? It's convection because the mantle is a fluid. It has the ability to flow. So here we now have a driving force pushing to the left and a driving force pushing to the right. Is this a very big force? Oh, you better believe it is. All right. So let's take a look at what's going on up top here. Oh boy, it's going on a lot longer than I thought it would. Okay. So on the top here, I'm going to take the whole top crust, the top layer, and I'm going to see that I have one being pushed this way and one being pushed that way. Well, hang on a second. How are they being pushed? It's just one piece. Okay, so picture this as there's a boat here and a boat here, and underneath the water is moving this way and the water is moving this way. So what's going to happen is this entire plate is being pushed apart and it's going to crack. I guess that's not a good crack, is it? There we go. So it cracks. And when it cracks and they move apart, this now is going to be separated and I get a gap the further it moves apart. And if I have a gap and all of this hot magma, it wants to be pushed out, what's going to happen is it comes out, cools, and then turns into rock. So what I have is here new rock formation, and an example of this would be the Mid-Atlantic Trench. So basically underneath the Atlantic Ocean is basically new rock forming. That's one thing. Okay. But what if we have one plate going this way, and from another convection current, we have another plate coming towards it? Oh, by the way, these are your plate boundaries. So these are tectonic plates on the top. They're plates that are floating on top of the mantle. Okay. So this would be what's called a diverging boundary. It's a divergent boundary because it's diverting. It's going away. Okay. So what would happen if I had two plates coming together? One going this way and one going that way. All right. If these are my two plates and they're coming together, when they meet, I could meet with equal density in those plates. And what happens now is they keep pushing and they move up. And what happens there is I get enormous mountain ranges like the Himalayas. Let that marinate a second. That's not the bad one. Okay. Mountain ranges are good. Okay. However, what happens if this plate has a very high density and this plate coming in is weak and it's easy to crumble and break? Well, what happens now is it pushes and this plate is going to push back harder and it crumbles and subducts underneath. So basically what happens here is the boundary now goes underneath the mantle and it becomes hot enough when it reaches the bottom that this is now going to reach such high temperatures and pressure that you are now going to produce a mountain range that comes up. However, all this pressure is going to come up with it, and you produce volcanic mountain ranges. Volcanic mountain ranges. Can you think of an example of where there's a volcanic mountain range? Well, I'll tell you, almost all of the northern Andes mountains. So in South America, you have a lot of volcanic mountain ranges. These are tough. So much pressure builds up under here, you have very explosive volcanoes. Here, at a divergent boundary, they're not very explosive because they're moving apart slowly, and the magma can come out nice and easily. So this would be something like in Iceland, okay? Or the Mid-Atlantic Ridge, where they're just separating and they slowly come out. However, if you do not allow the magma and pressure to be released, then it builds up pressure, builds up, okay? And eventually it's going to burst through. And when it bursts through, it's very, very explosive, okay? And the longer it builds up, the bigger the explosion, the bigger the eruption is going to be. So, divergent boundary. This is a convergent boundary, both of these because they're coming together. This is a subduction boundary because it goes underneath. Okay, so I'm going to tell you another story. Some of you might know this already, some of you might not. So I have gone cross country, and one of the interesting things when I was cross country was when I went to Yellowstone National Park. If you think about Yellowstone, Yellowstone is in what state? The great state of Wyoming. Wyoming, maybe yay big, and up here in the northwest corner is Yellowstone. And Yellowstone Park is basically going to look like that. Okay. Yellowstone Park, I found out something very interesting about Yellowstone Park. Now again, if you've seen this before, you know where I'm going. If you have not, well, this is going to be a very big eye-opener. While I was at the park, there was a lake, a big old lake, okay? And what happened in this lake is there were trees, meaning the tree line was in the lake. Now, is it normal for trees to be growing out of a lake? No, it is not. So how the heck could this be happening? Well, the reason is this. Here's the ground. And here are your normal trees. Give me time to put these trees on here. Okay. As your trees just sit right here, and then the lake would normally have been over here, what happened now is it tells you a little bit about the landscape and what's underneath Yellowstone. So what's underneath Yellowstone is a giant cauldron. It's probably not spelled right, but whatever. Okay, this cauldron is basically a whole bunch of heat and pressure of magma building up, pressurizing, getting bigger and bigger and bigger and bigger. Okay. As this gets really big, what it did to the ground is it bulged the ground up. So it lifts it as if it were ready to blow. Okay. The lake that was on top of it, now, due to gravity, has moved. Okay. What does that mean? That means that this is just a huge cauldron that is pushing the ground up. Okay, here's the eye-opener. When you look at a volcano, normally, okay, this is your basic idea of what a volcano is going to look like. So you have all of the magma coming up here, all the churning and bubbling inside here, comes out to the top, blah, blah, blah. And then it cools, right? Some of it runs down over here, it cools and it builds higher and higher. Okay, the opening to the volcano is called the caldera. Okay, here's the eye-opener. This, at Yellowstone Park, is a volcano. It's referred to as a supervolcano. Technical terms, right? With this supervolcano, the caldera to this supervolcano is Yellowstone Park. Take that in. Yellowstone National Park, so the whole northwest of Wyoming, is the opening to this volcano. This volcano has erupted 600,000 years ago, or 200,000 years ago, something like that. It has erupted, and when it erupted, it left such a mark on the United States that the ash that came out of this eruption was found in dinosaur bones as far as Nebraska and Tennessee. All right, let that marinate there because that's a tough one. So that means that this eruption, all of this rock went up into the air and traveled so far that it landed in Tennessee. All right, so I don't want to try and scare you, but if you have heard of Yellowstone, then you know what I'm talking about. If you haven't heard of it, look up Yellowstone supervolcano and you'll know what I'm talking about. I wish I was there to tell you about this because this is a really interesting story and poses a huge threat to the U.S. if it ever did go off. Because think about it, if it did go off, all of that ash, we're talking about millions of tons of rock that are going to be blasted into the sky as ash. That ash blocks the sunlight, the temperature of the earth drastically drops. We are in what would be an ice age. So if you think you're safe in New Jersey, think again. If you think you're safe in Portugal, think again. Also, no sunlight coming in, then you don't have any plants either. So the whole United States is out of luck. All right, so anyway, I don't want to get too dark here. Not that I have already. So that's Yellowstone volcano. There is an enormous amount of pressure being built up from Yellowstone. Another dumb story to go along with this. When I was at Yellowstone, as I was walking through the hot spots, all the geysers that they have up there, everything was kind of roped off. And I was wondering why everything's roped off. So there's a little dock, not a dock, but a wooden, I guess a wooden planked area that you can walk over the hot springs. Now remember, these hot springs are heated by the underground heat from the core, ultimately, and the mantle. So they're very, very hot springs. So I was wondering, why is everything roped off? This is crazy. What happened? Apparently something did happen. And the weekend that I was there on, I think, a Sunday. So that Saturday, apparently somebody was on there with their dog. The dog jumped in. So what did the guy do? He jumped right in after it. Now that water is really, really hot. The dog's dead. And the guy had, I don't know if he passed away. I didn't really hear about what happened to the guy. But he did jump in. He had third-degree burns all throughout his body. And the only reason that the guy would be okay and not the dog, I mean, the dog was a little tiny dog. It was dead instantly. But the guy has a lot more mass, and it would take a lot longer for his temperature to change. Huh? You like how I did that full circle? Yeah. So, anyway, that's why everything was roped off, because the guy jumped in after his dog, who was already dead. Okay, moving forward. What I have for you then is, that's pretty much the way I'm going to end it. I'll just say that is temperature change and everything that there is to know about heat transfer. And what day is it today? Well, I'm making this on Tuesday. You'll be seeing this on Wednesday. Thursday is going to be our little mini test on work and energy. So make sure that you're on there. And after you're done reading this or listening to this, watching this, whatever, leave comments, and I'll ask you, give an example, give your own example of the 3 forms of energy transfer. 3 forms of energy transfer. So you got conduction, convection, radiation. Give 3 of your own examples of how you can change the temperature of something by way of conduction, convection, and radiation. Okay? And that is all for now. Stay safe.